In this video, we review different types of functions that you would have looked at in grade 11. So we'll go through the different functions that you would have looked at. Hopefully they're all familiar. If not, not to worry, because we will dive deeper into many of these functions, most of these functions, in fact. So here we go. We'll start with polynomial functions. Now, polynomial functions you may not have heard as a term to describe a type of function. They describe an entire class of functions, basically, and we'll have a look at those to begin with. So I'm going to start with one that you're very familiar with. I'm going to start with a linear function. So y equals x. Y equals x. And we'll graph that on the grid roughly. We know that it goes through the origin, it's a straight line, it kind of has a slope of 1, and it looks something like this. So that's considered a polynomial function, and we'll dive deeper into what makes a function a polynomial function later on. The other type of polynomial that you know, so sorry, let's add this in here. This was called a linear function, so linear. And you'll notice here the domain is that x can be anything, the range is that y can be any value. Y is an element of the reals, and you can see that this function is increasing and so on, and you can describe characteristics. So the other polynomial functions that you should be fairly familiar with is the quadratic function, which looks sort of like this. And again, I'm just drawing it rough here, so you'll see that things don't quite match up on the grid, but it's just enough to give you a rough idea here. So this is y equals x squared, or f of x equals x squared, and we called this a quadratic function. Now there are many other types. Those are the types of polynomials, that you've looked at so far. There are many other types. So there's one that might look like this. And again, I'll just kind of do this roughly. This would be y equals x cubed. And hopefully you're starting to see a little bit of a pattern here. We would call this a cubic function. Don't worry, we'll spend some time looking at cubic functions in the first unit in the course. And then we can kind of get into some other functions that maybe look like this. And this would be an example of some of what we call a quartic function. So it would be, y equals x to the 4 with a whole bunch of other terms in here as well, whatever those happen to be, like an x cubed term. There might be an x squared term, an x term, and a constant term. I've left out coefficients just because it'd be hard to kind of make those up on the fly. And this is what we would call a quartic function. And you can see really with these polynomial functions, the exponent here on the highest power of x is just really going up by 1 every time. And so we can keep doing that indefinitely and get more and more and more polynomial functions. So for example, we could have a function that looks like this, and so on. And again, as I said, we'll spend some time looking at these polynomial functions a little bit later in the course. So let's talk about rational functions. Rational functions, let's try that again. They are the ones that look like y equals, let's see if I can move that graph. Here we go. They look kind of like this. I'll maybe draw it out over here. They have a horizontal asymptote and a vertical asymptote. Oh, I didn't do a very good job here. The idea is that this should get closer and closer to the x-axis, and this over here should look sort of like this. So we have a vertical asymptote here. I'll just use VA for vertical asymptote just to simplify that a little bit. And we also have a horizontal asymptote over here. And again, I'll just use HA for now. So that's what that would be. The equation for this function would look something like y equals 1 over x. And just a reminder, we get that vertical asymptote, this vertical asymptote, as a result of not being able to put x in the denominator as 0. So remember that it is impossible, it's not possible for us to have a denominator of 0. That creates a situation that's undefined. We take 1 and divide it by 0. That's not possible. And so we get what's called the vertical asymptote here. X cannot be 0, which creates this asymptote here. So the curve will get infinitely close on both sides but never touch. And we also have a horizontal asymptote. And we'll talk more in detail about this a little bit later on. So a key feature here are the asymptotes, something that was different for you. Asymptotes. All right, let's move on to the next one. The absolute value function it looked sort of like this. Oh, let's try that again. I'm having trouble with my mouse. Here we go. So the absolute value function looked sort of like this. It looked like a straight line from the origin on up. And then we actually had, oh, hang on a second. Let's fix that up. There we go. And then we also had a reflection of that straight line in the y-axis. All of the y values, sorry, in the x-axis, all of the y values should be positive here. So anything that was negative gets reflected in the x-axis, giving us this sort of V shape. So the equation here might have been something like f at x equals the absolute value of x. So just a reminder, the absolute value bars, these bars right here, just tell us to take whatever number is inside the brackets and make it positive. Whatever the final result is, we just throw away the sign and make it positive. With absolute value, we're really interested in the magnitude and not so much the direction. All right, what else do we need to know about absolute value? That's probably good enough for now. Let's also move on to the square root function. So the square root function looks sort of like this. So again, the square root function is where we're taking the square root of an x value, and the graph would look sort of like this. Let's see if we can draw that. So just a reminder, we can't yet take the square root of a negative number, but so for now, and I seem to not be able to see that. Oh, here it comes. Hang on just a second. All right, so let's try this again here. You know what? I might just get rid of that graph because it seems to be causing some problems. So the idea here is that we have our axis, our x and y axes, origin right here, and the graph kind of does this. So we can't take the square root of a negative number. So the domain of this function is that x has to be greater than or equal to 0. So that's the square root of x. So that gives us this kind of starting value here, if you will, and we take the square root. So the square root of 1 is 1, the square root of 4 is 2, and so on, so we would get these values. So that is the square root function. Let's move on to the next one here. Let's see if our graph will work this time. So the exponential function is something like y equals 2 to the x, or f at x equals 2 to the x. And again, you can make a table of values if you really wanted to, but that graph will look something like this. Well, 2 to the 0 is just 1. Just a reminder, exponents of 0 give us 1. 2 to the 1, I'll space things out a little bit. Here is 2. Well, maybe I won't space them out too much. 2 to the 2 is 4, and you get this kind of graph that looks sort of like this. It grows very quickly as x becomes larger, certainly to the right of 0. So key feature here is that there is this horizontal asymptote here where the y values get closer and closer to 0 but never actually touch it, because 2 to the exponent of 0 can never equal 0. So the function here would be something like f at x equals 2 to the x. And you could have a different base here. 2 is a common one to use. We could have a fractional base, and we'll talk a little bit about that later on. We could have 3 to the x. The only difference here between y equals 2 to the x and y equals 3 to the x is y equals 3 to the x will grow much faster. It will still have this same point right here, and then instead of going to 2, it will go to 3, so you kind of get this kind of behavior that happens. And things are getting a little crowded there by the x-axis. So this one was y equals 3 to the x. All right, and the sort of last type of function that you would have looked at in grade 11 would have been trigonometric functions. And again, there were a few of those that you looked at, so we'll maybe drew a few different graphs here to have a peek at. Let's see. Well, maybe I made 3 of them, but I think maybe you only did 2 of them, so we'll save the third one for when we get to the trigonometry a little bit later on. So let's get rid of that one. And the trigonometric functions were things like y equals sine x and y equals cos x. So again, I'm just going to kind of sketch those out for you. And y equals cos x. So then the interesting thing about these functions is that they are periodic, which means that they repeat. So the sine graph starts here at the origin. I'm going to say start. We'll move to the left in a minute. Oh, hang on a second. You can't see that. No, I don't think you're going to be able to see that. Let's try again, though. All right, we're going to get rid of that graph. And we're going to try one more time. Somehow the layering is not working very well for me, so just give me a second here, and we'll try again. So let's try and see if that fixes it. Alright, so the idea is that we would start here at the origin, graph comes up, hits a maximum, comes down, and then again it repeats this process forever. I'm going to try this one more time and see what happens. It does not want to move. We'll just draw our own set of axes and go from there. And again, it does continue on forever in the negative direction as well, so we get this kind of behavior that goes on and on. It does have an absolute maximum for the standard function anyway at 1, and an absolute minimum of -1. And the period is the length of time it takes for one full cycle. So one full cycle takes 360 degrees. We will spend a lot of time in the course talking about these trig functions. So if you don't remember a whole lot, that's all right. We will get there. So that was y equals sine x. Let's have a quick peek at y equals cos x. Very similar graph. In fact, the cos graph is really just a shift of the sine graph by 90 degrees. And instead of starting at 0 when x is 0. When x is 0, y is 1. And the graph kind of does this sort of thing. As I said, it's just a shift of the sine graph. So this is our y equals cos x. And again, it has a maximum of 1 here and a minimum of -1. So those are the different functions you would have looked at in grade 11. A quick kind of review of those functions, just to kind of get you thinking about those functions again. As I said, we will touch on pretty much all of these functions, perhaps with the exception of the absolute value in the square root function. We'll spend a lot of time looking at the other functions in great detail.